Let's review what we talked about last time. Let's review what we know about force. And then let's review what we know about the characteristics of a force. So force, think about what that is. It is a push or a pull, compression or tension. It is external stuff, acting on the outside of a thing, and it is measured in, what, pounds. Okay, now the three characteristics of a force. Well, there's the point of application, there's a place where you apply it. What else has it got? It's got magnitude, how many pounds is it? And it's got direction, and the direction is made up of angle and sense. So point of application, magnitude, how big is it, and direction, what angle is it, and what direction is the arrow pointing. Those are the three characteristics. Last time we said that when you draw a picture of a force, however big the force is, that's how long you draw the arrow. So if it's a 500-pound force going straight up, you draw an arrow 500 units long going straight up, and so forth. And we do that because a force is a vector quantity. It has not only magnitude but direction. Okay, well now what if we have to add forces together? And adding them together means, like with this motorboat here, we've got the force of the current and the force of the river. We want to know what those two forces together are going to add up to. What is the net result of those forces? To think about that, let's imagine two little kids pulling one of those red wagons, one of those radio flyers. And the handle came off, so they went and got some ropes. And they tied their ropes to the front of the wagon. And they're about equal size, equal strength, these kids. But they're little. Let's say they're 5. So they're not all that savvy on what direction to go. So one little kid pulls off to the right at 45 degrees, and one little kid pulls off to the left at 45 degrees. What direction is that wagon going to roll? Well, without doing any math, I bet you can picture that that wagon is going to go straight ahead, even though the kids are pulling at angles. And you would be exactly right. One little kid is pulling with 10 pounds, one little kid is pulling with 10 pounds to the right, one little kid is pulling with 10 pounds to the left, and the net result is that wagon's going to go straight ahead. How do we do that? We make a parallelogram around those two arrows. So this arrow can have another side parallel to it. The left arrow can have another side parallel to it. So we have two sets of sides that are parallel. And then we just connect the diagonal corners. And that diagonal is the resultant. It's the net result of those two forces. How big is that resultant? If you measure it, you will find out it happens to be 14.14 units long. So what that means is, if you had one kid pulling straight ahead with 14.14 pounds of pull, he or she would have the same net result as those two kids pulling off to the side. And that is a method called the Parallelogram Method. Well, we can apply that all kinds of places. Let's say we have a retaining wall, and we've got pressure from wet soil pushing against the back of the wall, trying to make it slide. Or maybe trying to make it overturn. Then we have the weight of the concrete pushing straight down, trying to resist the sliding or the overturning. What is the net result of those two forces? Well, we could find that by drawing a parallelogram around those two forces and figure out where the net result of those two things would land. And in this case, it's back about a third back from the toe, so this wall is going to be okay, as it happens. Well, let's think about that motorboat. And let's figure out what direction that boat is going to go across the river. So we'll do that by drawing a parallelogram. And what we know is that the river is 10 pounds pushing sideways, and the motor is 20 pounds pushing across the river. So if you were going to draw a picture of those two forces, it would look something like this. You'd have a 10-pound force, an arrow 10 units long going out to the side. You'd have a 20-pound force, an arrow 20 units long going up. Those are the two forces that represent, the two arrows that represent those forces. Now you might say, hey, wait a minute, isn't the river pushing at the middle of the boat and the motor's pushing at the back of the boat? Yes, but remember that principle of transmissibility? Our good friend, which says you can slide an arrow anywhere along the line of action and it will have the same effect. So what I did was I decided to slide this 20-pound arrow so that its tail was just touching the tail of the 10-pound arrow. Now I can figure this out. And what I do is I draw a parallelogram around those two arrows. Here's a 10-pound force and another side that's parallel with it. Here's the 20-pound force and another side that's parallel with it. And then I connect the corners of that parallelogram. And that diagonal is the net result of those two forces. That is called the resultant. So here at the top is a picture of our two kids and their 10-pound ropes pulling on that wagon, and how we drew a parallelogram to find the resultant, to find the net result of those two kids. Well, you might notice, hey, why do I have to draw all those sides? Couldn't I just make half of that parallelogram, make myself a triangle, and solve the thing? And you'd be absolutely right. Yes, you can. And that's a method called tip to tail, where you just draw half the parallelogram, and that's what we'll look at next.